Jainendra Jain for our institute colloquium. Normally we have colloquiums when we have full house or students, but this time when we realized the possibility of having him here, we couldn't resist, and we are having the colloquium live as well over YouTube. So thank you, Professor Jain, for agreeing to be with us. I request my colleague, Professor Abhishek Chaudhary, Head of Physics Department, to introduce the speaker.
Of course, Professor Jain doesn't need an introduction to the scientific community, but still for the purpose of introducing him, I will say a few words. It is with great pleasure that I introduce today's speaker, Professor Jainendra K. Jain, who is the Ivan Pug University Professor, Erwin Muller Professor of Physics, and holder of the Eberly Family Chair at Penn State. Earlier this March, Professor Jain was awarded the prestigious 2025 Wolf Prize in Physics for his groundbreaking contributions to quantum matter and its topological potential, transforming our understanding of two-dimensional electron systems under strong magnetic fields. In the late 1980s, during a postdoctoral appointment at Yale, Professor Jain introduced the concept of composite fermions, exotic particles in which electrons bind with quantized vortices. This elegant theoretical framework unified our understanding of both integer and fractional quantum Hall effects, what are now known as Jain states, and remain a cornerstone of condensed matter physics. His work has had profound implications, enabling the design of ultra-low resistance materials and advancing the foundations of topological quantum computing, as recognized by the Wolf Prize Committee. What may be inspiring for our students is that Professor Jain's journey began in a small village in Rajasthan, India, overcoming significant personal and physical challenges, including a childhood accident and a lifelong disability. His perseverance led him to IIT Kanpur, a PhD at Stony Brook, and faculty roles at Stony Brook and Penn State, culminating in this year's recognition. He is not only a bold theoretician, but also an inspiring mentor, credited with over 250 influential publications, a seminal monograph, and numerous honors, the Oliver Buckley Prize in 2002, election to the National Academy of Sciences in 2021, and foreign fellowship in the Indian National Science Academy in 2025. Today, as we welcome Professor Jainendra Jain, let us celebrate both his extraordinary scientific insights and his remarkable journey. Please join me in giving him a round of applause. Professor Jain.
Does this work? Well, thank you very much for the introduction. So when you look at this, you see a bunch of letters, numbers, and symbols appearing in some random. Okay, so you just saw, is it working now? Okay. So you just saw a sequence of some random numbers, random letters, and other symbols appearing in some order, and it of course makes no sense. But if somebody gives you the key, the encryption key or the password, then you can just read it. Okay, and in some sense, theoretical physics is not so different from this. So nature presents us with lots of experimental facts, which at first seem kind of puzzling, disconnected. And the idea of condensed matter theory or theoretical physics in general is to find the decryption key or the fundamental principle that can impose some sort of coherence on all of those facts and also bring out the underlying message. So of course, that's a recurring theme in all of physics. You know, this is what happens everywhere. But today I'm going to talk about this particular system, two-dimensional electrons in a strong magnetic field. And we'll see that the study of this topic has taken us into a strange new universe where the standard rules of quantum mechanics that we had learned are not useful. You know, you have to come up with new ideas. And in particular, we'll see that this system has strange or bizarre quantum particles which are not allowed to exist in three-dimensional world according to laws of quantum mechanics. So I'll basically tell you a story. It has many surprising twists and turns. I'll tell you what they are. And in fact, and in particular, the unfolding of the mystery of the fractional quantum Hall effect. From a theoretical perspective, it's a problem that's impossible to solve, as I'll try to convince you. But there is a key. There is an encryption key, and that's the particle called composite fermion. I'll tell you what motivated this. I'll tell you what, how it helped us understand the fractional quantum Hall effect and other related phenomena. And of course, the field still has twists going on. You know, in recent years, there were surprising new discoveries, and hopefully there'll be more as time goes by. So in this talk, I will try to eliminate all the technical details to the extent possible. So it's supposed to be for someone who is not familiar with the topic at all. The idea will not be for me to dazzle you with my mathematical prowess, but rather to amaze you with the power of ideas and with the beauty of quantum mechanics. Okay. So the story in some sense began about 150 years ago when Mr. Hall discovered what is known as the Hall effect now. So of course the Ohm's law was known prior to that, but he performed the experiment in the presence of a magnetic field, and he discovered that when there is a current flowing in certain direction, of course there is a potential drop along the current path, but there is also a potential drop across the current path. So he called it the Hall, I mean, it's called the Hall voltage. And one can define a new resistance. It's Hall voltage divided by the current. It's called the Hall resistance. From simple classical electrodynamics, one can derive that the Hall resistance is given by the expression here. B is the magnetic field. Rho is the density of charge carriers, and E and C are fundamental constants. So if you plot the Hall resistance as a function of the magnetic field, you find the straight line. The slope of this actually gives you the density of charge carriers. This is like the standard way to measure the density of charge carriers. In fact, this is how people discovered holes, because sometimes it has the wrong sign. So for about 100 years, this was tested in hundreds of labs around the world until in 19 Okay, until I think this was in 1980, so for about 100 years later, Klaus von Klitzing performed the experiment in two-dimensional systems. So these were MOSFETs, silicon MOSFETs, which we all have in our iPhone or smartphone. So what he found was that instead of this straight line behavior, the Hall resistors has these plateaus. And more importantly, he found that the Hall resistance on these plateaus had a universal value. So it's given by an h divided by an integer times e squared. It does not depend on any details, okay? It does not depend on which sample you are studying, how big the sample is, what's the shape, size of the sample, how much disorder you have, okay, to a certain extent. And as far as we know, this formula is exact. So it's been tested to about 10 significant figures. So this was very surprising. At the same time, the longitudinal resistance goes to almost 0. So it's not 0, but it's exponentially small. So this is known as the integer quantum Hall effect. Integer because this quantity here in the denominator is an integer. And Klaus von Klitzing received the Nobel Prize for this in 1985. So the question is, what's happening here? Okay, so let's look at the problem quantum mechanically. So in the absence of a magnetic field, we know that the kinetic energy is a continuous function of energy. So we have particles at any arbitrary kinetic energy. But in the presence of a magnetic field, the kinetic energy takes some quantized values. So very naively, you can understand it in the following way. In the absence of a magnetic field, the electron goes in a straight line. In the presence of a magnetic field, if the electron were a classical particle, it would just execute circles. Quantum mechanically, the orbits get quantized. So only certain kinetic energy values are allowed. And these values are called Landau levels. In fact, the quantum mechanical solution tells us how many electrons you can cram in a given Landau level. It's called, it's equal to the magnetic field divided by what is called the flux quantum, phi naught, defined here, per unit area per Landau level. So essentially, each flux quantum penetrating the sample creates one state, one allowed state in each Landau level. So now we can start filling these Landau levels. And once we have run out of electrons, we count how many Landau levels are filled. That's called the filling factor. It's density divided by this quantity. Sorry, for some reason, my throat gets dry very rapidly, so I'll keep drinking some water. Hopefully that's okay. All right, so in general, we have a lot of ambiguity as to where to put this electron. But when the filling factor is an integer, okay, so this is the origin. So let's start by switching off the interaction between electrons. In that case, we find that when the filling factor is an integer, we get a unique ground state. So it looks like this. For filling factor 1, we fill one Landau level completely. And that's it. That's the wave function of this state is precisely known. For filling factor 2, we fill 2 Landau levels. For filling factor 3, we fill 3 Landau levels, and so on. When we switch on the interaction, the gap survives unless the interaction is too strong. But at least it survives to some extent, and that fact is responsible for the integer quantum Hall effect. So I'm kind of pushing under the rug the fact that we also need some disorder, but for the purposes of this talk, that's not important. So this is the physics. Okay, somehow this. So this is the physics responsible for the integer quantum Hall effect, and this is a phenomenon that's very well understood. So what is the origin of the integer quantum Hall mystery? Well, this is the solution. That's what gives us to integer quantum Hall effect. Okay, so let me also mention that in 2016, Haldane and Thouless won a Nobel Prize for a topological interpretation of the integer quantum Hall effect. So another twist in this field came just maybe a couple of years later when these three gentlemen here discovered a plateau where we see a fraction 1/3 rather than an integer. So this is the 1/3 effect, you might say. And Robert Laughlin, he wrote a beautiful wave function to describe the state. And for this work, Sui, Stormer, and Laughlin, they won the Nobel Prize in 1998. But it turns out that this is only the beginning of the story. So, you know, once experimentalists know something interesting is happening at in some region of parameter space, they try to improve the experiments. And within a few years, the fractional quantum Hall effect started looking like this. So now you see there are lots of plateaus. And each plateau, of course, comes associated with a minimum in the longitudinal resistance. So either you can look at the plateaus here, or you can look at the minima. So there are lots of different fractions. And you know, this is what the resistance looks like. So this, I often say, is the most beautiful single trace ever taken in physics. So this is just the resistance as a function of the magnetic field for a two-dimensional system. This may look like noise, but it's not noise. It's perfectly reproducible. And it's beautiful because, as we shall see, we can understand all little details showing up here. The fractional Hall effect, I would say, is among the most stunning manifestations of quantum mechanics at the macroscopic scale. And it's also one of the most striking mysteries that nature has produced in quantum condensed matter physics. Now, I was talking about experimental facts, right? These clues, you know. So there are lots of clues here. So if you count the number of fractional Hall states, I mean, remember, there is one associated with each minimum. So there are about 100 of those. Experimentalists can measure various properties of all of these states. You know, they can measure gaps, for example. They can measure various transport coefficients like thermal Hall effect. They can do the experiment in different systems, graphene, quantum wells, etc. So there's lots of data available. There is data available associated with Raman effect, optical experiments, etc. To this we can add lots of computer data that theorists can produce. So we can put some number of electrons, let's say 18 electrons, on the computer, diagonalize the problem exactly, and obtain spectra that look like this. And we know the eigenstates and eigenenergies, you know, all of these for lots and lots of different systems. So this is akin to data of quantum chemistry, you know. So there's a huge amount of information that's available to us. Okay, now let's come to theory. So let's just think about the problem from a theoretical perspective. Forget about the experiments for a moment. So the minimal model for fractional quantum Hall effect would be as follows. So the full model has kinetic energy, interactions, Zeeman energy, and disorder. I'm going to imagine there is no disorder, and I'm going to imagine that I consider the limit of extremely high magnetic fields. In that case, the first term and the third term, which are proportional to B, they become much larger than this term, which is proportional to square root of B. So we minimize the first and the third terms by placing electrons in the lowest lambda level. So this is the kinetic energy, I minimize it. And we assume that electrons are fully spin polarized. And in that case, these terms become constant. We throw them away. And the minimal Hamiltonian has this form in appropriate units, which has to be solved within the space of the lowest lambda level. So notice that there are no parameters here. There is no mass. There is no kinetic energy. Okay, so what do we want to do? We would like to identify the fundamental principle underlying the fractional quantum Hall effects and to develop a microscopic theory that explains, unifies, predicts, and also enables parameter-free calculations. Okay, that's the objective. From experiment, we know that at certain special fractional values of the filling factor, we expect unique gapped ground states, just like we did for integer quantum Hall effect. Now, if you switch off the interaction at any filling factor less than 1, we don't get any unique states. So it's something like the situation here. So suppose we have 64 states in the lowest lambda level. If we have 64 electrons, of course, we put 1 electron in each, and we are done. We get a unique state. But if we have fewer than 64 electrons, then you can arrange them in many different ways. So you get, you get many different possibilities for the ground state. So a model of non-interacting electrons cannot explain the fractional quantum Hall effect. Now, moreover, this is the most strongly correlated system in the world. So typically, we measure the strength of correlations as the ratio of the interaction energy to the kinetic energy. This problem has no kinetic energy. So therefore, it's the most strongly correlated system in the world. I might also say right now that there's no exact solution to this problem known, and I don't think there'll ever be an exact solution. Now, of course, that does not worry us condensed matter physicists. Even the problem of 3 interacting electrons cannot be solved exactly. So if you insist on exact solutions, then all condensed matter physicists might as well go home and choose a different profession. One can make a lot of progress without exact solutions. But the problem here is that there is no small parameter either. There is no parameter, period. So all of the perturbative schemes that we rely upon in other contexts, they are of no use here. Now, just to get a feel for what we are dealing with, let's count how many possibilities are available to us. So if we take a system of 100 electrons at, let's say, a filling factor 2/5, so that's 100 electrons in 250 states, we have 10 raised to the power 69 different configurations available to us. If we take 1 billion electrons, which is typically the number of electrons in an experimental system, we have 10 to the power 8 times 10 to the 8. I mean, this is a number that human mind cannot really grasp. Just to give you a perspective, if you ask, if you put into ChatGPT the question, how many quarks are there in the universe, the number is something like 10 to the power 80. So these are very large numbers we're dealing with. Of course, no computer would ever be able to diagnose this problem. But we have no idea where to begin. So we have so many possibilities, we don't know where to begin. So this is, that's why I say this is an impossible problem, just from a theoretical perspective. Okay, so one has to look at the experiments. So it's sometimes said, and it's always true actually, that question is more important than the answer. The most important thing is to ask questions. In fact, the art of theoretical physics is to ask the right question at the right time. So if a question is properly defined, sharpened, then it often has the answer in it, or at least it gives you the clue to the answer, it points you to the answer. I mean, this is something that all of us, who are doing research, we kind of know. You have to define the question. So let's ask some questions. You could ask, what's the physical origin of the fractional Hall effect? What's the organizing principle? What's the mechanism of the fractional Hall effect? I mean, these questions are not particularly illuminating. I mean, these are all different ways of asking what's happening. Okay. Well, a more interesting question is, what are the weakly interacting emergent particles of the fractional quantum Hall effect? Now, this might seem a little strange. Why should there be weakly interacting emergent particles? But if you think about it, this is actually almost a rule of nature, that whenever you have strongly interacting particles, they combine to produce weakly interacting particles of a different kind. So that's why quarks combine into neutrons and protons. You could take, let's say, some quarks and electrons, put them in a bucket, shake the bucket, open it, you might find helium-4 atoms, which are much, much more weakly interacting. So this happens at all levels in nature. This is still not the sharpest question. We have one more step to go. So if you ask, suppose we do have some weakly interacting emergent particles, what would they do? Well, the only thing that the weakly interacting particles can do here is to show integer quantum Hall effect. So you could ask the question, can we understand the fractional quantum Hall effect as the integral quantum Hall effect of certain emergent particles? Now, this is something that had bothered me for a while. And earlier I said you have to ask the right question at the right time. So right time is also important, because you cannot answer the question before the time is right. So just to give an example, superconductivity was discovered in 1911. And Einstein was in full form at that time. He was at his peak. But now we know in hindsight that there was no way he could have answered that question, because we know what was required to answer the question, and those things were not known at that time. So I used to come back to this question every once in a while, and actually, let me motivate this question from another perspective. And to drive home the point, I'm going to erase all the numbers from here. And if I do that, you notice that this single plot has both integer and fractional quantum Hall effects, but you cannot really tell which is integer, which is fraction. So this is integer, this is fraction, but they have identical experimental manifestations. So therefore, it seems very natural that there must be a way to unify these two effects. So, okay. So before I tell you what the answer to this question is, let me acknowledge profound intellectual debt to a lot of work that had been done in the 1980s. Really beautiful, contributions which played an important role in this thinking, in my thinking. In particular, the work by Laughlin, which I mentioned already, but Halden, Halperin, Arova, Schiffer, Wilczek, Gerwin, McDonald, etc. Okay, so so what's the answer? So it occurred to me suddenly in late 1988 that if I introduced a new class of particles, which I called composite fermions, shown here pictorially, then I could make sense of many of the experimental observations. So a composite fermion is defined as the bound state of an electron and an even number of quantized vortices of the wave function. But in a pictorial sense, one can think of a composite fermion as the bound state of an electron and an even number of magnetic flux quanta, and that's this picture here. So this is a composite fermion carrying 2 flux quanta, this is carrying 4, and this is carrying 6. What does it do for us? So the intuitive picture, intuitive physics of composite fermions is shown here. So we postulate that each electron captures 2 or 4 or 6 flux quanta to turn into a composite fermion. And the composite fermions can be taken as weakly interacting. To begin with, you can switch off the interaction between them. The key property of composite fermions is that the flux that they have bound is not observable to them anymore. So they see the residual magnetic field. It's called B composite fermion. It's given by the expression here. It's the original magnetic field minus the field that they have assimilated unto themselves. Composite fermions then form their own Landau-like levels in this reduced magnetic field. So we are now going to think of them as ordinary fermions, except that they see this reduced magnetic field. So they have, they form Landau-like levels. These are called lambda levels. Their filling factor can be obtained, can be defined in this fashion. So this is the same formula I use for filling factor of the electrons. The residual magnetic field can point both up or down. So sometimes they can eat more magnetic field than it's available. So in that case, the effective magnetic field is pointing downward. We can use this expression and this to write a relationship between the electron and the composite fermion filling factor. So either this equation or that. So that is the intuitive physics of composite fermions. So if for experimentalists, this is all they need to know. Okay, let's also write a microscopic theory. So this is called composite fermionization. So I'm first going to go to the effective filling factor, nu CF. And here I'll construct wave functions of non-interacting electrons. So of course, here we have non-interacting particles, so we know all solutions. We know ground state, excited states, and so on. So I'm going to arrange these solutions, let's say in order of increasing energy, label them by alpha. Now we have to attach flux quanta or vortices to them, which is done through multiplication by this factor. It's called the Jastrow factor. Zj is like a complex number. This is the coordinate in the two-dimensional plane. So this is essentially my wave function, but it's not in the lowest lambda level. So I'm going to project this wave function by hand into the lowest lambda level and declare that this gives me the wave functions of strongly correlated electrons at filling factor nu in the same order of energy. So the ground state here will give me the ground state, the excited states will give excited states, and so on. So notice that this single equation provides ansatz wave functions for all eigenstates at all filling factors. You can say, how can a single equation give all wave functions? Because it's actually a mapping, okay? Furthermore, when nu CF is an integer, we get a unique wave function for the ground state. Remember, this is a unique wave function. So, remember that we had an enormously large degeneracy in the absence of interaction, or enormously large degeneracy if we look at the problem in terms of electrons. But when I look at it in terms of composite fermions, I find single solution. And also these wave functions, they look simple, but actually to implement them on the computer took us many years. But now we can do it pretty straightforwardly. We can work with systems which contain as many as 400 particles. Let me also just mention, and I won't do more than mentioning it, that there's also a field theoretical way to treat composite fermions. This goes under the name Chern-Simons field theory of composite fermions. Okay, so the composite fermion is a quantum particle. Why is that? So let's look at a vortex. A vortex has the properties, so a particle Z sees a vortex at eta because if it goes around eta, it gains a phase, or its phase gains 2 pi. A complete loop gives you 2 pi. And that's independent of the path so long as it's going around eta. If it does not go around eta, then the phase does not, phase comes back to the original value. So the vortex is a topological object. Of course, it has to do with quantum mechanical phases. And a single vortex is like a complicated, all electrons participate in the definition of a single vortex, because at that vortex, all electrons would see a phase of 2 pi. And for the same reason, a composite fermion is also a quantum mechanical, topological particle, and even a single composite fermion is a collective bound state in which all electrons participate. So therefore, it's natural to ask, do composite fermions really exist? And if so, in what sense do they behave as particles? How real are composite fermions? That was the title of a paper by Horst Stormer. Now, we theorists often find our theories extremely compelling. We fall in love with our own theories. But of course, experiments have the final word. Theories need to explain experimental facts. And also they to be really compelling, they have to make non-trivial predictions that are confirmed by experiments. So let's ask, what do composite fermions predict? What do they explain? Now we'll see that this theory successfully predicts or explains thousands of facts in a supremely unified fashion. So I will mention some of those successes, but these are kind of categories of successes. So each of these successes is equivalent to testing lots of different predictions, as will become clear. So the first is origin of the fractional quantum Hall effect. So let's consider these fillings. At these fillings, let's ask what is the filling factor of composite fermions. So using a formula that I had shown earlier, we find it's an integer. And therefore, here we have unique gapped ground states. So for example, 1/3 filling maps into filling factor 1 of composite fermions, 2/5 maps into 2, and so on. Just like an integer Hall effect, now if I switch, we assume that the composite fermions are non-interacting, but of course there is some residual interaction between them. But one can expect that the gap would survive when the residual interaction is switched on, unless the residual interaction is too strong. Okay, so this tells us what the origin of the fractional Hall effect. Why is there a gap at all at any fractional filling factor? This gives a picture. Second success is it tells us what the prominent fractions are. So here I want to show you these slides, this set of slides that was that I inherited from Horst Stormer. So these are the same figures. Remember, each minimum corresponds to a fractional Hall state. So we have integers here. When we go to somewhat higher magnetic field, we start seeing fractions. So notice that all of these fractions, they correspond to this formula that we have here with where we have chosen 2m, which is the number of vortices bound, equal to 2. At yet higher magnetic fields, we see these fractions, which again follow this with 2m equals 4. Now, what we will do is, or what Horst did, was to take the upper panel and plot it as a function of the magnetic field seen by composite fermions carrying 2 flux quanta. So remember, BCF is equal to B minus something. So I have moved the upper panel leftward by that something, okay? So the effective magnetic field, or the magnetic field as seen by composite fermions, is 0 here, and here so here it's, so I have plotted it as a function of BCF. Now you notice that there is the 1/3, 2/5, 3/7, all of these fractions aligned with integer fractions. So this looks just like the integer Hall effect of some particles. So one might as well remove these fractions and replace them by integers. These fractions, which are higher order fractions, they completely align with these simpler fractions here. But I can take the upper panel, move it further toward left, and understand all of these as integer quantum Hall effect of composite fermions carrying 4 flux quanta. Okay, so the fractional Hall effect at these filling factors is equivalent to the integer Hall effect of composite fermions. And these are the fractions which are seen most prominently in experiments. So we have already seen fractions corresponding to composite fermions carrying 2 flux quanta and composite fermions carrying 4 flux quanta. There is also experimental evidence for composite fermions with 6 and 8 flux quanta, as shown here. Lots of fractions are seen along these sequences. So here, these sequences, they have seen up to 10 members of these sequences, or 6 members of these sequences of composite fermions carrying 4 flux quanta. In fact, as they make samples better and better, they see more and more. So in the best quality samples, they have seen up to 14 or 16 members of these sequences. The same sequences occur in monolayer graphene or bilayer graphene. So you can see this is fractional Hall effect. So it doesn't depend upon which material you are looking at. Okay, some of you may know that the field has been electrified recently because it's become possible to see fractional Hall effect without applying a magnetic field in certain twisted bilayers or pentalayer graphene, but they still see the same sequences. So there also we have composite fermions produced in the absence of a magnetic field. So the conclusion here is that the theory correctly predicts the observed fractions, and the fact that they appear in certain sequences. These fractions exhaust almost all of the 100 observed fractions. Notice that all of these fractions are explained in one fell swoop. Okay. The theory also unifies the fractional and the integer Hall effect, and the new fractional Hall effect in zero magnetic field, which is known as the fractional quantum anomalous Hall effect. Theory produces, so the integer quantum Hall effect of composite fermions produces only odd denominator fractions, as you can see here. Indeed, most of the fractions are odd denominator. So even denominator fractions are not disallowed, but they would occur because of the residual interaction between composite fermions, and therefore they are expected to be much weaker. And notice that we haven't needed any microscopic theory so far. Okay, so this was one success, but of course the success is such that we have explained lots and lots of fractions. The second category of success is going beyond fractional Hall effect. So here what we do is we subject the theory to a stress test. We apply it to some extreme limit for which the theory was not originally intended. So here we take the limit p goes to infinity, which of course correspond to electron filling factor equal to 1/2. A puzzle here had been that no fractional Hall effect was seen here. So, one of the questions was, 1/2 is the simplest fraction. Why no fractional Hall effect here? Now, composite fermion theory says that here, when electrons convert into composite fermions, they swallow all of the magnetic field. Nothing remains, and therefore we get composite fermions in zero magnetic field. They form a metal or a Fermi liquid. A metal has no gap, and therefore no fractional Hall effect is seen here. So this is something that's been tested and confirmed in lots and lots of different experiments, which I won't go into, but okay, it's fully confirmed, and even up to this stage, we don't need any microscopic theory. Most of this can be understood from the simple picture that I showed earlier. Next, we go to microscopic validation. So what I'm going to do here is to do two independent calculations and put them on the same plot. One calculation is to obtain the exact spectrum by a brute force diagonalization of the Coulomb interaction. No approximation here. The second calculation would be to take the composite fermion theory and calculate the spectrum from it, again without making no approximations. And neither of these two theories has any parameters. So we'll compare the two. So let's take a system at filling factor 3/7 as an example. And here I'm showing you the largest system that can be studied here numerically. It has 18 particles. This shows the exact spectrum. So in this case, a nice geometry is to wrap the two-dimensional electron system onto the surface of a sphere with a radial magnetic field pointing outward. A natural quantum number is the total orbital angular momentum, which is the x-axis. Here, we are looking at only the extremely low energy part of the spectrum. So for example, at this angular momentum, the total number of states would be around 1.4 million. We are showing just some of the very few states. All of the structure you see here, so you see that there are these bands they are forming. This is coming from interaction. So if I switch off the interaction, all of these states would collapse into the same energy. All will have zero energy. Okay, so just to drive, I made this point already, but the state here, if I write it in terms of basis functions, then I need to know around 1.7 million coefficients to define the state. Okay. So what does the composite fermions theory say? Well, it says that this is depicted by this cartoon here, three filled lambda levels, but there is a precise wave function associated with this, given here. And these states are particle hole excitations of composite fermions, so excitons. There is, of course, no adjustable parameter here. Even here, once you fix the quantum number, you find there is a unique state. So we just take these states, calculate their Coulomb energies, and we get these dots here. So you can see that there is an amazingly good agreement, okay? In fact, this is what I mean by cracking the code. So for example, if you do exact diagonalization here, you have 2.3 million numbers. Computer will give you 2.3 million numbers, and you could stare at those numbers until the end of the universe. You have no idea what they mean. But what composite fermion theory is telling us is that this state can be written in this fashion to an extremely good approximation. And once I see this, I say, aha, it's three filled lambda levels times this Jastrow factor. So it's three filled lambda levels of composite fermions. So you know what this actually means. Well, after you stare at this for a while, you say, well, there is some discrepancy here, small discrepancy, and how about these higher bands? Well, we can consider excitations with higher kinetic energy. So this is one kinetic energy excitations, but I can add two kinetic energy excitations, and we can diagonalize the Hamiltonian in this subspace, and we find that these numbers become almost exact, and we can explain higher and higher bands in a very systematic fashion. Okay, so this is a quasi-whole quasi-hole is a missing composite fermion. A quasi-particle is an extra composite fermion. In these plots, I'm showing exact density profile of a quasi-hole and a quasi-particle, and also what composite fermion theory predicts. You see only one curve because they lie on top of each other. Now, I'm not doing any cherry picking, so you can take any filling factor. So this is filling factor 1/3, 2/5. You can take filling factors in between. This is what you get all the time, okay? So for all systems in the lowest lambda level for which exact diagonalization has been performed, the composite fermion theory correctly predicts the quantum numbers of the low energy eigenstates. It almost exactly predicts their energies and their wave functions. And we have tested thousands of eigenstates. Okay, so it's kind of a miracle. The infinite choices of the electron problem disappear when we view the problem in terms of the composite fermions producing unique solutions, and a single equation gives all low energy eigenstates at arbitrary fillings. In fact, when this happened initially, we were flabbergasted because we never expected these wave functions to be so accurate. We thought we are going to get something in the right ballpark. We never expected that these would be the solutions. And still, people ask me, why are these so good? And I don't know why they are so good, but at least this proves without any doubt, this is like a microscopic confirmation of the existence of composite fermions as you can get. Okay, so they are as real as Cooper pairs. So far the physics that we have learned is this. We have integer Hall effect, and as we go to higher magnetic fields, we have fractional Hall effect, which can be seen as integer quantum Hall effect of composite fermions. And at filling factor 1/2, we have a Fermi liquid or a metal of composite fermions. Another class of bizarre particles that we see here are called anions. So some of you may know that in 2 dimensions, it's possible mathematically to define particles which are neither bosons nor fermions. When you exchange 2 particles, you get, if you, for fractional Hall states, if I take this quasi-particle, one here, if I exchange 2 of them, I get a phase factor where theta star is given by this expression here. So I'm not deriving this, I'm just telling you this result. It can be derived without too much difficulty, but not in the time that I have here. So if for bosons, theta star is equal to 0, and for fermions, it's pi, modulo 2 pi. But this is neither, so these are anions. Anion is the name given to particles with any statistics. This is a topological property of the excitations, and it actually had been appreciated prior to the composite fermion theory as being a consequence of a state with a gap at a fractional filling. So this was first noted by Halperin in 1984. And recent experiments have shown evidence of anions. So it has taken quite a long time before this property could be actually experimentally confirmed. Okay, so there are numerous other successes. So once you start thinking in terms of composite fermions, you can add lots of other states to this family. So we have talked about integer Hall effect and metal, but they can form stripes, they can form crystals, they have superconductors. So I will have a little more to say about this. There are bilayer states. They can show their fractional Hall effect as well. And one can test lots of different things, different properties of all of those, which I won't go into. Okay, so okay, this was a poster prepared by when I gave a talk at the Korean Physical Society meeting in 2017, and I say that the Koreans are well known for plastic surgery. Okay, so they did something to make me look much younger than what I looked in 2017. But the main point here is that if you look at the lower right-hand corner, you would find that there are electrons which are interacting with one another, holding hands, but they are not particularly happy about this. They are unhappy electrons, frustrated, but then they let go of one another and capture two flux quanta instead and turn into happy composite fermions. So this was a cartoon that had been prepared by Kwan Park, who did this when I was a student in my group. He's now a professor in Korea. And often I don't like to show this slide, but I end up showing it. The reason I don't like to show this slide is because I have this uneasy feeling that a year from now, if you remember anything from this talk, you will probably remember this slide and nothing else. But I show it because I feel if you remember anything, I have succeeded, So, okay, so let me say we have spent an inordinate amount of time in making quantitative comparison with experiment. So as I told you, we can go to very large systems, obtain thermodynamic limits for various quantities. We can include effects coming from things like finite quantum well width or lambda level mixing and so on. And okay, so there's a lot of work here which I won't have time to talk about. You can look at some of these books which have articles by experts on this. How much more time do I have? 5 minutes? Okay, so let me try to finish this within a few minutes. Let me quickly tell you, so I have given you one mechanism for fractional Hall effect, which is as the integer quantum Hall effect of composite fermions. A second mechanism is superconductivity of composite fermions. So it turns out that there is an even denominator fraction which has been observed. It's 5/2. In fact, by now, there are many even denominator fractions which have been observed. These, of course, cannot be understood as integer Hall effect of composite fermions because that gives us only odd denominators. So what's happening here? Well, these emerge from a composite fermion metal when the weak residual interaction between composite fermions causes them to form pairs and thereby opening a gap. The paired state has been modeled. So there are certain wave functions that go under the name Pfaffian or Parton wave functions. But they have one aspect which is not completely satisfactory, which is that, so if you remember Bardeen-Cooper-Schrieffer wave function for superconductivity, it contains some variational parameters, so you can adjust it a little bit, and the Bardeen-Cooper-Schrieffer wave function also gives a Fermi or a metal in one limiting case. These wave functions don't have that flexibility. So we have recently tried BCS theory of composite fermion pairing, And let me very, very quickly just mention what we find. We find, okay, I won't go through the details here. We find that at filling factor 5/2, indeed, this state, indeed we find that there is a pairing instability into p-wave pairing of composite fermions. We have also looked at, okay, so at filling factor 1/2, I said there is no fractional Hall effect, but in fact, if you make the quantum well wider and wider, at some point you start seeing fractional Hall effect. So this is a phase diagram plotted as a function of quantum well width and the density. And as you increase quantum well width or the density, you start seeing a fractional Hall effect state. We have modeled that in terms of a Bardeen-Cooper-Schrieffer wave function, and let me just say that we find the red region to be described by a superconductor of composite fermions. The blue is a metal, and this is the experimental phase boundary. So the theory actually can explain experiment quantitatively to rather good precision. Okay. Let me just mention one more particle, which is Majorana particle. And that, so Majorana particle is a solution to Dirac equation that was discovered by Majorana about 100 years ago. No fundamental particle in nature is a Majorana particle, at least it's not known. But it turns out that this was a point made by Reed and Green or Moore and Reed, that the composite fermion superconductors can produce Majorana particles. So essentially, the abricos vortices are Majorana particles. You know, they're their own antiparticles. These have 0 modes trapped inside, and they actually, in this context, obey non-abelian statistics. So each Majorana can be thought of roughly as half of a composite fermion, and if you take 2 of these, they can either add to no composite fermion or they can add to 1 composite fermion. So it has been predicted that, or it has been proposed that one can use these Majoranas to make a topological qubit. And if you could do that, it would be fault tolerant. And there's a lot of work going in this direction. In fact, this has motivated Majoranas in other contexts. It's been predicted that semiconductor nanowires, which are proximity coupled to ordinary superconductors, would have Majoranas at the 2 ends. And in fact, recently there was this news that Microsoft unveils Majorana 1 chips, the world's first quantum processor powered by topological qubits. This is controversial, but certainly, you know, a lot of work is going on in this direction, and we'll know soon, or hopefully we'll know soon whether this works or not. But let me just say, okay, so you can read these things. You know, there are some things which are still to be done, but from my perspective, the 2 things that I would love to happen would be for composite fermions to be harnessed for future technology, for example, through Majoranas. You know, it can take quite a long time before fundamental physics can give rise to technology, but you know, it can happen. And the other thing that would be amazing would be if composite fermions could provide a crucial clue to unravel some other fundamental puzzle in physics. You know, so for example, the Higgs mechanism, which was first found in superconductivity played an important role in the standard model of particle theory. So maybe this would also happen, but this is a dream at this stage. So with that, I conclude my talk. Let me also show a lot of wonderful students who have done all the work here. And in particular, Srijit and Ajit Balram, I showed many of their work here. So with that, I would like to thank you for your attention. Please.
With questions or comments?
So is there also a simple way to understand the widths of these plateau states?
So
In a simple way, because they seem to be like having sort of a random widths.
yeah, it's not random. So let's say for integer Hall effect, in the simplest case, where disorder is, let's say, particle hole symmetric, plateau, the nu equals 1 plateau would go from filling factor half to 1 plus to 3 halves. And the next one would go from 3 halves to 5 halves, okay? So if you take this 3 halves and 5 halves and convert this into the filling factor of composite, so you take that to be the composite fermion filling factor,
Yeah.
that's where the plateau.
I see.
So plateau extends between nu CF half to 3 halves, 3 halves to 5 halves, and so on. So that's been tested very precisely, actually.
So I have one more question. So this nu equal to 1/2 state where there is no leftover magnetic field now, is there any other experiment that can actually test that Fermi liquid of the composite fermions other than the Hall, the plateaus in the Hall?
Oh, there are lots of experiments. So here what happens is, so if you had a classical electron, it would go like this. A composite fermion goes in a straight line. So one of the most dramatic tests here is the following. Let's say you go slightly away from filling factor 1/2, okay? So if you had a classical electron, it sees a large magnetic field. It executes very tiny orbits. A composite fermion sees a small magnetic field, so it would execute huge orbits. So these orbits have been measured in many of these experiments, and they find that the radius of the orbit is consistent with BCF.
Okay.
In fact, so there are these experiments where you inject composite fermion through one constriction, and you can catch it through other constriction. So that tells you what the radius of the orbit is. And sometimes you find that the composite fermion orbit is going in the direction which is negative to the direction that the electron would take, because they see negative effective magnetic.
Okay.
So this has been, this was actually taken as a direct confirmation of, direct observation of composite fermion.
Thank
Okay,
you.
so it's
Thank you.
been tested in lots of different experiments. You could say it's like imaging. So this kind of experiments had been done for electrons, these. So I guess you could say that. So it's, it's, okay, so it's, I think the imaging in some sense will come soon, because now they can do, they have been able to do STM experiments in these systems, recently. So this is Ali Yazdani's group at Princeton. So for a while, people didn't know how to do STM on this, but now they can do it. So I think they would be able to image some localized composite fermions. But here it's more like you're playing billiards with composite fermions, but you can see the trajectories, but you cannot see individual composite fermions in these experiments. Okay.
Could you comment on the role of the disorder? Because most real samples will have some kind of disorder.
Yeah.
And you said that it is important, but you will ignore it and so on.
Yeah, so it's kind of somewhat ironic or very interesting that you need disorder to see quantum Hall effect. And the reason is that let's say for integer Hall effect or for non-interacting electron, this is something that's extremely well understood. And the reason is that disorder creates localized states except at the center of the plateau or center of the, except at one energy where the states are extended. And as the chemical potential moves across the localized region, the Hall resistance does not change. And so it remains quantized. So this is needed to explain the existence of plateaus. Now it turns out that, so in fractional Hall effect, when you have interacting electrons, you don't know how to address this problem. But in terms of composite fermions, if I say I have non-interacting composite fermions, the whole physics we have for electrons can be transported over there. So in fact, this was a beautiful experiment by Avik Bid. So we did some calculations, and even without calculations, one can expect, just by the analogy between the fractional and the integer Hall effects, that the exponent that characterizes the divergence of the localization length would be the same in integer and fractional Hall effects. So here, for a long time, people were doing experiments. Mansoor Shaigan at Princeton, he had done this, and he found that the exponents were different for fractional Hall effect than they were for the integer Hall effect. But what Avik did was, so for this experiment, okay, for some technical reasons, even in the integer Hall effect, you have to make sure that the disorder is short range. Okay, so if there is long range disorder, it kind of becomes very hard to go into the critical region. But if you have short range disorder, then you can get into the critical region and measure the exponent. So Avik, he put some screening layers on the two sides. So this was a graphene sample. I think it was tri-layer graphene, but that's not important. So he could make the disorder short range, and beautifully the integer and fractional exponents come out to be the same. So there's quite a bit of understanding. But the role of disorder in integer Hall effect is the same as the role of disorder in fractional Hall effect in terms of composite fermions.
Is there any alternate way other than the composite fermions to explain the obvious?
No.
Is there any other way to look at it? People explored it, or once you give this idea of composite fermions, then everything starts moving in trying to explore out of this concept.
So before composite fermions, there was a hierarchy theory. So let's say you start from 1/3. So people knew Laughlin's wave function. So the idea was to keep doing Laughlin again and again. So the paradigm was Laughlin. In composite fermion theory, the paradigm is to integer Hall effect. That's the paradigm. But let's say we are not thinking in that way. So the idea was, okay, let's start from 1/3 and move away from 1/3. So we will have some quasi-particles. And then the idea was, okay, these quasi-particles could form their own Laughlin state at some point, okay? So if you do that, you can say this would happen at filling factor 2/5, which is the correct filling factor. The problem is impossible to imagine that you could continue this for like 16 over 33, so lots of these have been seen. In fact, so some assumptions are made in this approach, which is to say that the quasi-particles are such that two-particle interaction is dominating, and the short-range part is dominating. And both of those assumptions are not correct. Okay, so plus, when you go to filling factor 1/2, we have fermicy, which has to do with composite fermions. There's no other way to understand it. So if you look at the full picture, there's nothing that comes even close. So the previous ways of understanding, there was no quantitative confirmation of those of any kind. Okay.
Yeah. So I have two short questions. So first one is philosophical. So how did you came up with the idea that electrons or fermions will pair up with flux lines? Is it motivated by something like a BCS that two electrons can form a composite Cooper pair? And the second question is, for the case of composite fermion superconductivity, where does the attraction come from? Is it still the phonons?
Okay, so these are very good questions. So first of all, how did I think about composite fermions, right? So, okay, if you take this idea that the fractional and the integer Hall effects, there must be some connection. And so this idea that you bind flux quanta to electrons was there because of study of anions. So, so for those who don't know, this idea of anions was, it came about theoretically, just like a conceptual curiosity by Lynhorst and Merheim, who are two Norwegian scientists. And then Frank Wilczek later said, well, you can model these anions as electrons with some fractional value of flux associated with them. It was believed that if you put two flux quanta, you get back the same electrons. So that gives you nothing new. So everything is kind of periodic. If you say you want to combine integer and fraction, then this, okay, if you think about it for a while, you might convince yourself that this is not so unnatural. It's kind of a natural thing to think about, okay? So with that question, but if you are not thinking in that question, then you won't come up with composite. The second question, where is the attractive interaction coming from? It's, the idea that somehow you get superconductivity from purely repulsive interaction is something that's very appealing to a lot of people, especially in the context of high temperature superconductivity, where people would like to understand it without using phonons. So here is an example where we get superconductivity from purely repulsive interactions. So remember the Hamiltonian that we had just had the Coulomb interaction. But the thing is that, so you might ask, how can we have superconductivity? We have just purely repulsive interactions. The thing is that it's not superconductivity of electrons, but of composite fermions. So you have to ask, what is the interaction between composite fermions? Now, it turns out that the interaction between composite fermions is kind of a relic of the interaction between electrons. So if you change the interaction between electrons, you will change the interaction between composite fermions. The interaction between composite fermions, so in some sense, a composite fermion is an electron which is with a screening hole around it, which are these vortices bound to it. And you have to, they are very weakly interacting. Sometimes they can be weakly attractively interacting. It's completely possible. So the idea is that the only thing you can do is attach 2 flux quanta or no flux quanta. You cannot adjust this flux continuously. So sometimes this overscreens, okay, and gives you an attractive interaction. So the only way to see that is this BCS type calculation that we did. So we are actually changing, so as we make the quantum well wider, that's effectively changing the interaction between electrons, because, you know, instead of point particles, they become like disks interacting. And at some point, there is a transition into a paired state, which tells us that the effective interaction between composite fermions has become attractive. So this is a beautiful example where you start from a repulsive interaction, but the relevant quasi-particles have some attractive interaction, and therefore they form pairs. Okay?
Could you explain a little bit more about the Chern-Simons Foundation for Composite Fermions? Because as I understand it, it's coupled to a statistical gauge field.
Yeah.
And so how do you control the fluctuations of the field in
The fluctuations in the B field.
in the gauge field, in the statistical gauge field?
Yeah, so in that, okay, so in the Chern-Simons approach, what they do is they do a Chern-Simons transformation, which attaches an integer number of flux quanta to each electron. So, you know, the wave function that I wrote, I have vortices attached to electrons. In their case, at the mean field level, you are attaching flux quanta. So that means, you know, this Jastrow factor, Gi minus Gj squared. In that approach, there would also be a denominator, which is modulus of Gi minus Gj squared. But in any case, what you do is a mean field theory. So you start with this. You have to keep the kinetic energy term. You do a mean field theory. And then whatever is left, you treat it perturbatively. The problem is there's no small parameter. But you say anyway, you do perturbation theory. You calculate.
What about near compressible states, like V equal to 1/2?
It's the same problem. So one of the difficulties is there is no control parameter. But you say, okay, I know how to do RPA. A fundamental law of physics is that you do what you can do. Okay. So you know how to do RPA, so you do RPA. You have some result. You say, does it make sense? Compared to experiments, if it works, then it's good. Otherwise, you say we have to calculate corrections. Okay? So that's the way it proceeds. So we don't have, for example, you know, R. Shankar has this RG type justification for, Fermi liquid. That is lacking in this. So it would be nice to have. But again, that's a matter of a control parameter, which we don't have. So, you know, these wave functions that I showed, we don't know what Feynman diagrams you have to sum in the field theory to give these wave functions. So, in fact, one of the problems of the field theory is that it cannot even get the correct units, you know, because it has the electron mass in it. And you cannot get rid of the electron mass if you just do things honestly. You know, so in wave function, I just say I'm going to project. You know, so that's part of my ansatz. But here you start, you have electron mass, which is not a parameter of the problem. But all answers will have electron mass. So, okay, so, yeah.
Thank you, sir. So I was asking, while you were telling about the success of the composite fermion theory, you mentioned about some recent studies in the absence of magnetic field. So in that case, how are these quasi-particles now defined in the absence of field? Or if now we are plotting, initially we were plotting against the applied magnetic field.
Right.
Now, what is the parameter here?
Beautiful. So, so first, you could ask, how can you see any fractional Hall effect in the absence of a magnetic field? So what one is doing in these experiments is somehow the band structure is encoding magnetic field in it. So magnetic field is frozen into the band structure. So at some level, you could ask, what is a magnetic field? So if you have looked at the Hofstadter model, magnetic field is nothing but if the hopping parameter has some phases associated with it, that's magnetic field. Okay, so in these systems, if you take bilayer, you twist it a little bit just by the right amount of right angle, then it turns out that the combined band structure of these things has complex phases, and it's equivalent to a magnetic field. Tight binding theory. So it's simple single particle theory. Now, the picture that I presented to you, where I say it binds flux quanta, would not be, okay, that would still be okay, but a better way to think about those experiments is to come back to the more accurate definition of composite fermion, which is an electron binding vortices. Because even in those systems, the wave functions are complex. Okay, they are not real. So there are vortices, and those vortices can be bound. Although let me point out that a quantitative theory of fractional anomalous Hall effect is not yet available. So in fact, these beautiful wave functions which I have in continuum, once you put a lattice or a periodic potential, we don't know how to generalize these. That would be something very interesting. I mean, that's a challenging problem, but we don't know. So
Functions are not applicable here. So block functions, when you're telling about the periodic lattice,
yeah.
So block functions will not be applicable here.
No, you have to put some block functions, but then how you attach vortices and so on, there's no simple prescription. I mean, this prescription I have cannot be simply carried over to those systems. Okay. Well, thank you for all these very nice questions. Okay.
Painting by no, not this one. This is the golden temple. Golden temple.
Oh, that's a golden temple. Oh.
In the location, there were some paintings by one of our colleagues.
Yeah, this is a place that my wife and I have been wanting to go to, but at least we have something.
Not far from here.
I know.
This is a mug which has the Isamohali logo on it.
Okay.
And this is a book about the birds of Isamohali.
Thank you.
Favorite haunt of all kinds of birds that migrate north and south from Russia around and around.
I see.
They come here at different seasons of the year.
Thank you. Thank you very much.
So enjoyed your talk very much, and thank you very much again for coming.
It's my pleasure. Thank you.
Sir, this is the solicitation that on the 17th of April when we did talk. Thank you, sir. Thank you, sir.
Thank you very much.
Of IAPT and on behalf of Professor P.K. Ahluwalia.
It's my honor. Thank you.
So, sir, I want just one click with you.
Will you please send me some of these pictures?
Yes,
Thank
sir.
you.
Ahluwalia, sir, will send. I will